Okay, we'll now talk about Chapter 2, Section 2, which deals with density curves and specifically uniform distributions, but mainly the normal distribution. The normal distribution is a huge topic for us, and we're going to do a lot of normal distribution problems. So there's kind of a lot to cover, and so I hope you have a really good experience with the normal curve and with density curves. So first of all, what is a density curve? And a density curve is in essence a graph that represents a distribution. A distribution is just a list of numbers, and so it's just a graph. But we scale the graph in such a way that this is true. First of all, it is always at or above the x-axis, and the area under it is always equal to 1. So we scale the y-axis. So that's, and there's a lot of different kinds of density curves, but there's really two of them that we care about. One is the uniform curve, which means it's just going straight across. In other words, it's a rectangle. And then the other one is a normal curve, which is a bell-shaped curve, which we're going to use a lot of, that looks like this thing in this template that I have, and we will deal with that in a minute. But anyway, so the first thing we're going to look at is a uniform distribution. So uniform just means it's going straight across and making a rectangle. So our first context here, it says the time that Sven spends working on his homework each night follows a uniform distribution from 10 to 90. Don't get the word uniform mixed up with the word normal, and that happens a lot. Uniform means it's a rectangle. It's going straight across. So when you draw this distribution, it's just going from 10 to 90, so from 10 minutes to 90 minutes. There's our scaling, and so this is, the minutes in homework, we will say, just to properly label it, and it will be a rectangle. Okay. Now this rectangle is not going to be to scale because it's not going to be near that high because the area under it has got to be 1. So you would realize is that the width of this thing from here to here is from 10 to 90, and so that's going to be a total of 80 minutes. And so, the width times the height has got to be 1 because the area has got to be 1. So, the width times the height is equal to 1. And so the width of this thing is 80 times the height is equal to 1. So the height is 1/80th, which in fact is equal to 0.0125. So, which is 0.0125. And so that is the height of this thing, and that makes it a density curve with an area of 1, and that will allow us to make different calculations. Now, in these problems, you can sort of look at them in different ways, and it's mainly just dealing with areas of rectangles, and however you want to think about this, where you're getting the right answer is certainly fine with me. All right, so then we're asked this: what proportion of the nights does Sven spend studying more than 50 minutes? So every point in this rectangle represents a study time, the amount of time that he studied. And so this is a theoretical thing. Yes, there's an infinite number of points in there, but it's just a representation of the reality. So, in other words, what proportion of nights more than 50? Well, 50, here's 10 and here's 90, so 50 is going to be somewhere in here, right? You may initially see, hey, it's exactly halfway in between, and the answer is going to be a half. But what we're really supposed to do is we say to ourselves, what is the area in essence that is more than 50? Well, you would say, well, from 50 to 90, there's 40 spaces. So this shaded rectangle has a base here, or a width of 40, and then the height, as we have determined, is 0.0125. And so what is the area greater than? So we would just say the base times the height. So we'd say 40 times 0.0125 is equal to, and that's equal to 0.5, sure enough. So that is, in essence, one way to, do that problem. All right, and it says, what's the 25th percentile? In other words, what's 25% of the way between 10 and 90? And so there's different ways you could kind of think about this. You could say, well, the total width is 80. All right, so if I go 1/4 of the way, 25th percentile means 25% of the values are at or below this value. So we need, what is this value that contains 25%? So we could say, well, what is 1/4 of the way, or 0.25, times the total width of 80? And we do that, it's 20. So in other words, if we go 20 above this, 20 above 10, so plus 10, it would be 30 minutes. That would be the place on the graph that 25% is at it or below it, and there you go. So that's really all we're doing with uniform distributions. It just deals with areas. Now, the next thing we're doing is the normal curve. Now, a normal curve is this. There's a lot of distributions that we're going to have that follow a bell-shaped curve approximately, or a normal curve. And so in other words, like let's say here's the mean, which we're going to call mu, like that, is you are going to have a lot of values that are around the mean and not many that are sort of far away from it. So I'm going to make just a nice little bell-shaped curve here. Doesn't have to be the neatest thing in the world, and that one certainly isn't. But, and we're going to say that this is approximately normal. There's a lot of values that are around the average, and there's not many that are away from it. You know, theoretically, this thing never touches the x-axis. But anyway, and if we go out one standard deviation, we're going to go to this inflection point here in this graph. In other words, halfway down that hill. So if we go up one standard deviation and down one standard deviation, it's going to go about to there. If we go out 2 standard deviations, and we'll talk more about this in a minute, we'll go out to about here. It'll take about 95% of the curve. And then 3 standard deviations almost contains the whole thing. Okay, so in a normal model, it's really unusual to find anything that is above or below 3 standard deviations from the mean. And so the first thing to be aware of in a normal model, in any normal distribution, roughly, this is approximately, 68% of the values are within 1 standard deviation of the mean. 95% of the values are within 2 standard deviations of the mean, and 99.7% of the values are within 3 standard deviations of the mean. And so this is a rule that you have to memorize, okay? Now I'm going to show you how to use your calculator to do a lot of these problems, but you do need to be aware of this rule. All right? And so we have this situation. So let's look at this. So the weights of a large truckload of peaches follows an approximately normal distribution with a mean of 10, a standard deviation of 2. Use the 68, 95, 99.7 rule to find the percent of peaches that weigh more than 8 ounces. Now, first of all, because the normal distribution is a theoretical thing, and under that normal curve that we have here, under this normal curve, there's an infinite number of points. So it's impossible for any finite distribution, in other words, any real-world distribution, to be exactly normal. So whenever you describe something as normal, always say that it's approximately normal, because it's never going to exactly equal normal. All right, so what we're going to do is we are going to use the 68, 95, 99.7 rule. And so I'm going to draw the curve for this situation where, okay, every point on here represents, in essence, the weight of a peach. The mean of it is 10. So right here in the middle, is 10, okay? And 1 standard deviation. Now what that means is the average amount that these points are from the middle is 2, okay? And if we go up 2 standard deviations, it'd be 12. So any peach that weighs 12 ounces is 1 standard deviation above the mean. If we go up 2 standard deviations, that's going to be about to right here. So that's going to be at 14, and then 3 standard deviations, 16. A standard deviation below the mean is going to be 10 minus 2, which is 8, 8 minus 2, which is 6, and then 6 minus 2, which is 4. Okay, and so what the 68, 95, 99.7 rule says is this, is that 68% of the values are going to be between there and there. 68% of the points in this curve are between 8 and 12. 95% are within 2 standard deviations. And then 99.7%, or basically almost all of them, are between 4 and 16. It would be really, really unusual to get a peach out of here and for it to be more than 16 ounces or less than 4 ounces. Okay, what we're going to do these problems is that I'm going to find the area of each part of these things to answer the questions. And so I'll divide this in half first of all. And so between 10 and 12, well, this is in the normal curve is perfectly symmetrical. So there's 68% between here and here. That means there's 34% in each of these regions. Okay? And then what about between 6 and 14? That's within 2 standard deviations. So there's 95%. Well, what about the areas of this? Well, if you say 95% and you subtract off 68%, that in fact is going to equal to 27%. So, but there's two parts of it. If we divide it by 2, that's going to be 13.5%. So in this little area, there's 13.5%, and this little area, there's 13.5%. All right, then what about the next regions out here within 3 standard deviations? Well, if you say 99.7% is within 3 standard deviations, if you subtract off this minus 95%, that leaves 4.7% of the curve is going to be in these 2 regions, between 4 and 6 and between 14 and 16. Well, it's perfectly symmetrical, so if we divide those by 2, that is 2.35% that is there, 2.35%. So this is 2.35%. And then lastly, outside of 3 standard deviations, well, that's just going to be 99.7 is inside. So if we say 100%, minus 99.7%, and so that's equal to 0.3 of 1%. And then if we divide that by 2 for the 2 tails, that's going to be 0.15 of a percent, 0.15 of a percent that are on each tail. And so by doing that, now we can answer any questions that are being asked. So what percent of the peaches weigh more than 8? Well, weigh more than 8, you just add up all those areas. And so that's going to be 34%. And then from here on is 50%. So that's just going to be 34% plus the 50% that are above 10. And that, in fact, is going to be equal to 84%. Okay. What percent is between 6 and 12? So between 6 and 12, you would just add all these up. You would say, 13.5% plus 34% plus 34%, and that adds up to 81.5%. So that is the 68, 95, 99.7 rule for any normal curve would obey that rule. Okay, now to the main part of our normal calculations. So, all right, what do you need to do to show your work? Now, I'm going to show you a couple functions on your calculator that is going to do these very quickly, okay? And so we need to talk about showing your work. But in general, in the world of AP Stats, to show your work, if you're asked to show your work, all right, is you're expected to draw the normal curve with it scaled and shaded, and I'll show you that. You're expected to find the relevant z-score and then to find the answer, which is going to be the area of the curve. So that is in essence, what we're going to do. There's sort of some shortcuts with calculator syntax that I'm going to show you, but this is considered fully showing your work in regards to a normal curve. So here's sort of the main problem from a section, and calculators definitely, graphing calculators have definitely made this a lot easier than using the tables, but I'm going to show you how to use the tables for this. Okay, it says that the time it takes the workers at a factory to assemble a toy vary approximately normally. When we see that term, we immediately say to ourselves, this is dealing with Chapter 2, Section 2. Approximately normally, with a mean of 12.4 and a standard deviation of 2.1. If you randomly select one of the times, find the probability it takes less than 10 minutes. All right, so what we've got here, and so we've got these assembly times for toys, and so I'm going to draw the normal curve. Doesn't have to be the neatest thing in the world like that. And so I'm going to label it as normal. We're going to have a lot of different distributions in the world of stats, and so always label it what it is. This looks very similar to a t distribution, which we're doing later in the year, and other distributions. So always label your distributions. And then we have to scale it. To scale it, we're going to write the mean and then go up and down 1 standard deviation. Okay, and that gives us sort of a reference to look at. So our mean is 12.4. If we go up 1 standard deviation, that's this inflection point that's halfway down the little hill there. And so that would go to 2.1 plus that, so that's 14.5. And if we go down 1 standard deviation to this inflection point there, halfway down the hill, subtract 2.1, so that's 10.3. So thus I've scaled it. All right, now in regards to the shading, it says what's the probability it's less than 10? Well, 10 is somewhere over here. I'll just estimate that, so I'll just say, well, there's 10. All right, and it says less than 10. So that would be that shading. So this question is effectively asking, if I were to randomly select one of these times, one of these points under here, what's the probability I would get in the shaded region? All right, and so now what we're going to do, in order to use our table, that I'm going to show you. We've got to find the z-score for 10. We're going to use a z-score table to find this area. So our z-score, you may remember, is going to be our x value. Remember, it's x minus mu over sigma from section 2.1. And so in this case, it is going to be 10 minus our mu of 12.4 divided by 2.1. And that, in fact, is equal to negative 1.143, negative 1.143. And so intuitively, what a z-score is, it's the number of standard deviations my value is from the mean. So 10 is about 1.1 standard deviations below the mean. So this person was faster than on average, kind of significantly. But what proportion of people did he do better than? In other words, in essence, what's his percentile? And so we're going to go to the z-score table. So if you go to your formula sheet, you got these formulas, and if you turn a couple pages, you're going to come up with the standard normal probabilities. And you notice this normal curve here, and you notice that this table, this should be a shading here that you kind of can't see. There's a shading there, okay? So this table is going to tell us the area of the normal curve that is below a value, which is exactly what we need. But it's dependent, see that little letter there, I don't know if you can see it, on the z-score. That's a z right there. So that's what that table is telling us. And so what we would do is you notice these z-scores here that are on the left side, okay? And so notice on the left side, it has the ones place and the tenths place. And then on the top part, it has the hundredths place. So on this table, and so my value is negative 1.14 if I round it. So I'm going to go to negative 1.4, negative 1.1. So negative 1.1, which is right there, okay? And then what column do I go over to? Well, I go over the 0.04 column. So that would be negative 1.04, and I go down here, and I go over here. There it is, 0.1271. That is what that area is. In other words, it contains about 12.7% of the curve, okay? And that's the answer. And so, in essence, in a lot of times you'll see this notation, the probability that my x value is going to be less than 10, that is equal to the probability that my z-score is going to be less than 1.14, like that, and that is equal to 0.1271. And that is an approximation, by the way. That's an approximation. But, so there you go. And so this is saying if you were to randomly select a point under this curve, if you were to randomly select one of these times, what's the probability be less than 10? The probability your x is less than 10? Well, you convert it, you standardize it, as we call it. You standardize the value. You find the z-score, in other words, the number of standard deviations your value is from the mean, and then you use the table now, okay? Having said all of that, I certainly know that's very tedious. We're going to be able to, you do need to know how to do that, and that is fully showing your work, right there, fully showing your work. But you can also use a function on your calculator to do this called normal CDF. And I'm going to allow you to do this on a test. In other words, I am going to allow you to on any normal curve problem, to just write this and get credit for showing your work. But you could be asked to do this, and you will be asked to do this at some point. Okay, so you have to understand that. And so what we'll do, so the normal CDF function, and that stands for normal cumulative density function, all right? And so that is going to tell you the area of a curve, the area of this density function, all right? And so we will turn our calculator on, and it's under the distribution menus right there, which is right above the vars button. So to do a normal problem, you go right above the vars button, which it'd be so second vars, which is distribution. Then we have all of these things which we'll use in the future. We will never use normal PDF, never. That's one of the most common errors people use. They use normal PDF when we're going to use normal CDF. So the two big functions in this chapter are normal CDF and inverse norm right there. Those are the two big functions. So I go to normal CDF. Okay, now, and in some calculators, this screen doesn't pop up. I'll talk about that in a second. All right, so the lower value. So what we're entering into calculator is, we want to enter in, we're finding the area of this shaded region. Well, how far to the left does this shaded region go? It goes on to infinity. And so to enter infinity, what you could do, well, the easy thing to do is just go negative infinity. hit the negative sign is this button, not the minus button. That's a common error. This is the negative button, that's the minus. We use this for negative. So what we would do, so let's say the calculator just came like that. So we would say, well, I want to go negative infinity. I'll just go negative. So now it's negative, and then just enter like negative a huge number like that. That'll be fine, okay? Your calculator has negative infinity on it, but that for us is effectively, you got to realize, once you get below 3 standard deviations, which in this case is like, I don't know, like 8 point something or something like that, or 7. Once you get below 7, that thing is really close to the x-axis. So at negative 9 billion or whatever, it's insanely close. What's the upper part of my shaded region? It's 10. The upper part of my shaded region is 10, so I hit 10 for that. Mu is the mean. So that's mu, so I hit 12.4. And then the standard deviation of this thing is 2.1. And then I hit paste. Now, in most calculators, this is what's going to appear. Or in a lot of calculators. It's just going to immediately take you to that command. And then you would just enter the numbers in these order. So like in older versions of the 83 or the 84, it's just going to have this command come up. And you enter, negative infinity, all right, to 10. Mean of 12.4, standard deviation of 2.1. Now, you have to label those values. People forget to label those values. Label this LB for lower bound, UB for upper bound, and then mu and sigma, just as they, in essence, appear in your calculator. If you forget mu and sigma, you can just write the word mean and then write standard deviation. That would work. And then if we hit enter on this thing, if we hit enter there's the, and you notice this is a more exact answer, so we did some rounding with our other answer, and that's fine that the other answer we got is a little bit off, but so that's a more exact answer. So there's a full explanation. All right, so now let's find a couple other things. What if we're doing more than? What if we're doing greater than? All right, so now what we're doing, 15.8 is somewhere up here. So we could be asked to draw the curve and show the z-score and everything like this. We want this area. Well, the problem with using the table is it's always finding the area to the left. So in this case, what we're going to, so if we need the area greater than, what we can do is we can say 1 minus that. If like 30% is below a value, it means 70% has got to be above it. And this is a density curve, so it has an area of it under 1. So doing this using a table, what you would do is you'd find the z-score for 15.8. So that'd be 15.8 minus 12.4 divided by 2.1. And that, in fact, is equal to 1.62 approximately. 1.62. So then we would go to the table. Now it's positive 1.62. So this table A has 2 parts to it. The second part of table A is the positive z-scores. And so let's find, so we go down to 1.6, there's 1.6, and then go over to the 0.02. So, and then we go down here and over here. So that's 0.9474, okay? But we would realize this, that is the area to the left. That is, the table is telling us the area to the left, okay? And that is 0.94, now I've forgotten what it is, 0.9474. So the area to the left is 0.9474, but this wants more than that, not less than, so it wants this. So I have to say 1 minus 0.9474, and so that's going to equal to 0.0526, I do believe. And there you go. Okay, or you could do this, okay? You can use normal CDF, which is certainly the quicker way. It's slightly more accurate as well. So it'd be normal CDF. All right, so my value, my lower bound is 15.8. So that's 15.8. So the shaded region is to the right here. So my lower bound is 15.8 of my shaded region. My upper bound is infinity. So I write infinity. All right. My mean is still 12.4. Standard deviation is still 2.1. Like that. That would be actually considered fully showing your work. Unless, like I said, you were asked to draw the curve and show the z-score. But let's find that. And so what we'll do is we'll go second distribution, once again, second distribution, normal CDF, and we will go the lower bound of 15.8. The upper bound, just enter like 9 trillion or something. That'll work. That's certainly effectively infinity on this scale. Same mean, same standard deviation. Many calculators, that screen will just pop up, but anyway, it ends up being 0.0527 approximately, 0.0527, so that's pretty close. Once again, in the world of stats, most of the time, depending on the context, somewhere, 3 or 4 sig figs is good. Now, what about between 12 and 16? So what's going on here is we got this curve, it's centered at 12.4, and we know that like 10.3 is here, and that 14.5 is there. And so 12 and 16, so 12 is going to be somewhere around here, and 16 is somewhere up here. So there's 12 and 16. We need this area. So what that means is we will do normal CDF. So normal CDF from 12 to 16, our mean is 12.4, and our standard deviation is 2.1. Label this, lower bound, upper bound, mean, standard deviation. Here we go. And so normal CDF, second distribution, normal CDF from 12 to 16, mean of 12.4, standard deviation of 2.1, and so it's 0.5323. So 0.5323. And if you wrote all of that, that's considered showing your work. Okay, those normal CDF problems are kind of the heart of the chapter. But the other thing is what we call, in essence, using the inverse norm function. In other words, with these things, what is happening is they give us x values. These things are x values, these numbers in these problems, the 10, and they ask us to find areas. Okay, and then we can have the opposite. They could give us the area, and ask us to find the x value, such as in this. What is the 70th percentile? What that is in essence saying is we've got a normal model, we've got some value here, this x, that 70% of the values are at it or below it. So how can we find the x value? Okay, now, so one of the things you can do, and actually, I'm sorry, going back to this problem, if you're doing this by the table, what you would do is you would find the z-score for both of these values and find the area to the left of both these values and subtract those two areas to get that. So what we're going to do, using the tables to find the 70th percentile, what we're going to do is we will use this table to estimate the z-score for 70%, realizing these values in this table, all these values, it's areas of a curve. And so if we can find the 70th percentile, the 0.7, like you'll notice it's somewhere between these two values. Okay, right there on the table, that's 69.85%, that's 70.019%. So the z-score that goes with that is like either 0.52 or 0.53, roughly halfway in between the two. We could be really exact and try to prorate it, but you could actually go with either 0.52 or 0.53. I'll go with just halfway in between the two. So that's going to be 0.525. So that's my z-score. So my z-score is equal to 0.525. And that is equal to my x value minus my mean over my standard deviation, which is 2.1. And then I'll do a little bit of algebra to solve for x. And so, so we will say 0.525 times 2.1 is equal to, and then plus 12.4. And so that is equal to, my x is approximately equal to 13.50 minutes. And make sure to include the units. Minutes. There we go. Or you could use what is known as inverse norm, which is really the quickest way of doing it. So inverse norm is this. If you go second distribution and use inverse norm. So what inverse norm is going to do is you're going to be given the area of a curve or a percentile, and it's going to find the x value. And so I'm going to go, and a lot now, in the older calculators, it's just going to pop up and look just like that, but I'll talk about that in a second. So inverse norm, the area, and I always tend to go left area, and some calculators only give you the option of left area. So the area that's to the left of my value is 70%, 0.7. And then my mean is 12.4, and then my standard deviation is 2.1. And so I go down here, and so it's 13.50. Sorry, you may have not seen because of the glare there. So anyway, let me do that again. I don't know if you saw that because of the glare. So you would go, so what you do is you go second distribution, inverse norm, the area 0.7, there's the mean, there's the standard deviation, and so there it is, 13.50. 0.50. And so showing your work there is you could go inverse norm and then go 0.7, 12.4, and 2.1. Now, in some calculators, you would have to enter it like that. And you have the comma is right above the 7 button, by the way, if you would enter that. And so you would label this as left area, label that as left area, and label this as mu, and label that as sigma, and then you would get that. Answer. So now, okay, what time is less than 80% of times? So less than 80% of times. So we got this x value, and we got 80% that are above it. Okay, well, what does that mean? That means 20% that are below it. In other words, it's the 20th percentile. So if we're using left area, we would use 20%. So to do this problem, so we would say, okay, so this would be inverse norm, 0.2, mean of 12.4, standard deviation of 2.1. To get credit, we got to label these. This is left area. So left area, and then that's mu, that's sigma. Of course, you could go right area of 0.8 if your calculator has that option, but some don't. All right, and so what we'll do, second distribution, inverse norm of 0.2. There's the mean, there's standard deviation, left area. And so we get 10.63 approximately. So that would be 10.63 minutes. There we go. So that is how you do that. Okay, now, what is a standard normal curve? We define a standard normal curve as a normal curve with a mean of 0, standard deviation of 1. So that's sort of notation for a normal curve with an n. So mean of 0, standard deviation of 1. And it is in essence a curve of z-scores. So mean of 0, standard deviation of 1. So if we go up 1 and go down -1 to that. And so a standard normal curve is a curve in essence that we use to find z-scores. And so whenever we have to find a z-score to do a problem from a normal curve, we use the standard normal curve. It is a curve in essence of standardized values. In any normal curve, if you standardize all the values, in other words, if you found the z-score of all the values in the curve, like this, if we did that with every value and ended up with these z-scores, we would end up with a standard normal curve. Now, what is a decile? This is sort of a minor topic in the world of stats. A decile, if you know the metric system, it's a tenth, and so the deciles divide the curve up into tenths. So the third decile is in essence the same thing as the 30th percentile. So it means the third decile means there's 30% that's to the left. And so to find the third decile of the standard normal curve, that means mean of 0, standard deviation 1. It's a standardized thing. So we'll do inverse norm. So we'll inverse norm, 0.3, standard deviation of 0, mean of 1. So that is our left area. That is our left area. That is our mu. That is our sigma, like that. And so if we do that, and so here we go. So second distribution, and so we go inverse norm, 0.3, mean of 0, standard deviation of 1. And actually, whenever you turn your calculator off and on, it will reset to the standard normal curve, mean of 0, standard deviation of 1. And so we end up with negative 0.5244. In other words, using that would be the z-score that is at that point. That is the z-score. Now, if we do it with 0.9, so the ninth decile is the 90th percentile. Then that means 90% is to the left of it. All right, so it's inverse norm, 0.9, mean of 0, standard deviation of 1, left, area, mu, and sigma. And so if we did that, now, and by the way, if you hit second entry with your calculator, the enter button, if you hit second and then entry, it automatically enters the last command, or you could just arrow up there as well. And I can just go up here and change this like that. And so 1.28. So that's 1.28155. So those are the third and the ninth. So the third and the ninth decile are that. In other words, the ninth decile has a z-score of 1.28. It is 1.28 standard deviations above the mean. Okay, we're almost there. And Now, I hesitated to even do these problems because they're kind of tough, but this is about some of the, maybe some of the tougher problems we've had. These sort of things have been on the exam kind of as the harder problems that not many people got right, but I certainly don't want to underestimate anybody's abilities, and so I wanted to show you these problems. These are, in the AP Stats exam is a hard test, and you don't have to, we'll be talking about it, but you don't have to just nail every problem to get a good score. In fact, you can miss a lot of the problems and still get a really good score, but I certainly want to cover every type of problem that could be on the exam, and that's what we're going to do this year. So here's kind of some of the tougher ones. Anyway, so let's think about this machine. Let's think about this problem, rather, which is about a machine. All right. It says, a drink machine dispenses amounts of Dr. Pepper in slightly varying amounts. The amounts vary approximately normally with a standard deviation, there's our sigma, standard deviation of 0.12. The mean can be preset by the worker, so we don't know the mean. All right. What does the worker set the mean to if he wants a 12-ounce cup to be overfilled 1% of the time? So you have to recognize, it's approximately normal problem. So we've got this approximately normal distribution, like that, normal. Okay. And we don't know what the mean is. So there's mu. Okay. But we do know this. When you go up to 12, okay, so every one of these is a dispensing amount, in essence. We know here's 12 ounces. We know we want it to overfill only 1% of the time. We want it to go above 12 only 1% of the time. So what we've got here, whenever you have a problem where you don't know the mean or standard deviation, basically every time, you're going to be using the formula for z-score. Remember, the formula for z-score is x minus mu over sigma. So we're going to find the z-score for this point right here. How can we find the z-score? And then we'll plug it into this formula, and then we can solve that from u. Well, that's what we just did in that last problem. To find the z-score, we're going to consult the standard normal curve. So we would realize, well, if 1% is above it, that means 99% is below it. And so we will do inverse norm of 0.99, mean of 0, standard deviation of 1. Okay? And when we do that, we would let's see what we get. And so we will say second distribution, which is second vars. And so we go inverse norm of 0.99, mean of 0, standard deviation of 1. And so there it is, 2.326. So that is 2.326. And whenever you use the standard normal curve and inverse norm, it is telling you a z-score. It is a curve of z-scores. So this would be 2.326 is equal to, my x value is 12. I don't know the mean, and the sigma is 0.12. When we use our algebra skills to solve this, so we would in essence just multiply that times 0.12. So I'll just say that times 0.12 is equal to, and then subtract 12 from both sides, and I would get minus mu is equal to that. So therefore, mu is equal to 11.72, approximately 11.72, and the units here are ounces. And so that's how you do it, using the formula for z-score. Whenever you don't know the mean or standard deviation, it's a pretty good bet you're going to use the formula for z-score. So this one's a similar problem that has occurred. In number 9, the mean is set to 11.7. All right, however, the standard deviation is no longer 0.12. What would the standard deviation need to be if you want the dispenser to overfill 12-ounce cup only 2% of the time? So what we've got here is a similar situation, but in this case, we do know the mean. So it's going to be 11.7. And so right here is our x value. It's 12. We want this distribution to go above 12 only 2% of the time. Okay, well, that means 98% of this curve is below that. And so we'll find the z-score for 12, and then we will use our algebra skills with the formula for z-score to find what sigma is. So if we do inverse norm of 0.98, mean of 0, standard deviation of 1. So let me just enter that in here. So if what the heck, I'll just arrow back up to that and hit enter on it, and then just go change that to 0.98. And so the z-score is 2.05. So the z-score is equal to 2.0537. And now we can use the formula for z-score. So we would say the z, 2.0537, is equal to my x value is 12, my mean is 11.7, and then I'm trying to find sigma. And so I'll just use my algebra skills, multiply both sides times sigma here, and divide. And so I'd get sigma is equal to, in 12 minus 11.7, it'd be 0.3 divided by 2.0537. So it's just going to be 0.3 divided by that answer. So if I hit second and the negative sign, it comes up like that. And so it's 0.1461. So did I make a mistake there? So 12, and so, no, that's, so that would be, that's right, I'm sorry, 0.1461, and that has a unit that is also ounces. So, so that is that. And so, and then lastly is this, and I like incorporating this problem. This has been a problem, but frequently we get asked about outliers, and this is a good review of an important concept from Chapter 1. The ACT scores of students at a large school district follow an approximately normal distribution with a mean of 19.4 and a standard deviation of 3.7. What are the outliers? Remember our formula for outlier, which you have to remember. It is everything less than Q1 minus 1.5 times IQR, or anything greater than Q3 plus 1.5 times the IQR. Well, remember the IQR is Q3 minus Q1. So if we can figure out Q3 and Q1, we can enter them in here. Okay, and so that is that's what we'll do. Well, what is Q1? All right, Q1 is in essence the 25th percentile. Well, and that's what we've been finding with inverse norm. And so what we'll do to find the 25th percentile is, on a normal curve, is inverse norm of, and then the area to the left, it's 25% of the values are below it. So it'll be 0.25, our mean is 19.4, and our standard deviation is 3.7. So that is our left area, our mu and our sigma. So once again, we will go to second VARS, which is distribution. So if I go to second VARS, distribution, and go to inverse norm, and so this is 0.25, that will tell me the 25th percentile. In other words, Q1. And so our mean is 19.4 and then 3.7, 19.4, and so then this is 3.7, and so we're going left area as always, and then 16.904. So this is equal to 16.904. And then if we do what is Q3? Q3 is the 75th percentile. And so that is inverse normal 0.75, like that. And so if we do that, in other words, if we just go up here, hit enter, change this to 0.75, just like that, and hit enter, there's Q3, 21.8956. So 21.8956. Therefore, the IQR, the interquartile range, is that minus that, 21.8956 minus 16.04, and that in fact is about 4.991, I do believe. Okay, now we can enter these numbers into our formulas. So Q1, so if we enter it into this, so it's going to be anything less than our Q1 is going to be 16.904 minus 1.5 times 4.991. That is Q1 minus 1.5 times the IQR, which ends up being anything less than 9.4172. And these are test scores. They don't have a unit. So anything less than that is an outlier. Or using this formula, that's going to be Q3, which is 21.8956 plus 1.5 times 4.991. And so anything greater than that is an outlier. So anything greater than, that ends up being 29.3824 is an outlier. I know it's a lot, but that's it. And thank you for watching. I'll be glad to answer any questions that you have about any of this stuff. But, and that's it. And that's section 2.2. So anyway, we're also going to talk about, at the end of the chapter, it talks about assessing normality, and so, which isn't near as long a topic as this, and so we'll be talking about that in our next video. But thanks for watching. Have a great day.